No way.
No, that's so cute.
Morgan!
Greetings and welcome, friends. Today we're talking about inverse functions and relations. All my students are here except for one, but that's okay.
I love you, internet friends.
Yeah, we love the internet friends. So inverse functions are functions that undo each other. You might remember inverse operations. The inverse of addition was subtraction. The inverse of multiplication was division. The inverse of exponentiation was rooting, right? Stuff like that. Or I guess, never mind, I can't skip to that. That'll be next 2 chapters away. So the definition of inverse functions, here's this little thing. 2 functions f and g are inverse functions if and only if both of their compositions are the identity function. Now you might not realize what the identity function is. The identity function is the function that doesn't do anything. Just like the additive identity was 0, because if I add 0, it does nothing. The multiplicative identity was 1, because if I multiply by 1, it doesn't do nothing. The exponentiative identity was 1, because raising something to the 1th power does nothing. So, function composition, if f of g of x is equal to x, the function that does nothing just gives you back what you gave it, right? So f of g of x must equal x, and g of f of x must equal x. So let's work with this concept of inverses, functions that undo each other. We'll come back to that. Usually I use that part of the definition just as a check for inverses, but that's quite all right. So let's take a look at this example A. Example A, find the inverse function. So if f of x is equal to 3x plus 1, what do you think g of x would have to do? I'm going to put g of x over here.
Is that the inverse?
Yeah, if g of x is the inverse. Negative 3x minus 1, do you think that would undo all of that? Some other guesses.
I feel like more than 50, you just do the opposite.
And what's the opposite of multiplying by 3?
Oh, you divide
So 3 over
a third.
So 1/3,
minus 1?
1/3 x.
or like 1/3. Okay, 1/3 x minus 1. Okay, any other ideas?
Maybe what you were doing before x over 3.
Yeah, x over 3 is the same as a third of x. These are the same. Well, let's think about the order that this happens in. So this function here, f of x, what's the first thing that happens to x? It wakes up, gets out of bed. Does it go like grab a bowl of cereal? Does it take a shower?
It has to go pee.
Has to go pee. Classic. First thing it was multiplied by 3, right? And then what was the second thing that happened to it?
Wait, are we writing down these steps?
Yeah,
Real
yeah.
steps?
And then it was added by 1. That was the second part of its day, right? Add 1. So an inverse function not only would have to do the opposite of these steps, but it would have to do them in the reverse order, like diffusing a bomb.
It would be subtracted by 1 and divided.
So my inverse function would be subtract 1. Yeah, we've done something similar to this.
What was the opposite when I came into your IU block that one time when we did like the algebraic stuff?
Yeah, that was similar. Yeah, that was
Like,
using inverse operations to solve equations. Yeah, similar. So subtract 1 and then divide by 3. So not only do I do the inverse operation, but I have to do the reverse order, right? So it was like this way for this one, and then like the inverse was all like this way, right? So so in my anti-inverse world, first of all, does either of these functions do it in this order? No, what would the inverse function g of x have to be to have subtraction by 1? So what happens to x? It's subtracted by 1. So what's that look like?
Oh, x minus 1 over 3.
X minus 1
In parentheses.
in parentheses,
And then
all over 3, or 1/3 of in parentheses. Both of those are the same thing. Yeah, so I actually have to make sure that the subtracting by 1 occurs prior to the dividing by 3. Whereas in this case, I'm dividing by 3 first and then subtracting by 1.
Can't we just write the division sign and then a 3?
Like here? Yeah, but that's kind of like, we don't use the division symbol as often in algebra. We're more fans of like fractions and stuff. So as a check, I will tell you this, that this and this were not the inverse functions. G of x here in fact was. And to verify, let's figure out what is f of g of x. F of g of x. So that means, well, f of x was 3 times something plus 1. And g of x, yeah, sorry, was 1/3
I love that color.
of parentheses of x minus 1. So I'm replacing the x in f of x with an entire g of x, right? So that's what I've done. And let's calculate this now. So 3 times 1/3, what happens there? The 3 and the 3's cancel out, right? So I'd be left with, x minus 1, then plus 1, and then what happens with the minus 1 plus 1? Those cancel. So I get x. So that's good news. All right, that's what I kind of wanted f of g of x to equal, if they are in fact inverses. That's not enough proof. I also have to figure out what g of f of x is. And hopefully that's also equal to x if it is in fact our inverse. So g of x is 1/3 of parentheses whatever x is minus 1, right? So I've kind of set that up there. And what was f of x? That was the 3x plus 1. So I've replaced the insides of g of x with a 3x plus 1, whatever f of x was. So let's calculate this. Looks like I could do the plus 1 minus 1 first, right? And that cancels out, so I just have 1/3 of 3x. And what is 1/3 of 3x? X, plain old x, because the 1/3 of 3 is 1, and 1 times x is x. So it turns out these are in fact inverses. And one thing I'll point out is, if I didn't want to call this g of x, there's a different name I could call it because it was the inverse of function f. I also f to the -1 of x is the way we might write that, -1 being the, and you don't read that as f to the -1 of x. You read this literally as the f inverse of x is how you would say that out loud. And technically, that does make some sense why we might use to the -1st power, because you might recall, and I've got my math all over the place now, so I apologize for this, that say I'm multiplying by 2, right, something by 2, that's the same as multiplying by 2 to the -1. Or the inverse of that is multiplying by 2 to the -1, because I could move that downstairs. That would be the same as x divided by 2. So like this -1 power meant division in that case, which was the inverse of multiplication. So that's kind of where this notation comes from, but we use it for inverses of all sorts, shapes, and sizes.
Can you slow down for just a second?
Yeah, I agree.
Is your
Yep.
recall like the little house thing you found?
The recall was just a little blue thing here.
The little house thing you made?
Oh, can you remember?
Yeah, it's related to that. Yeah, properties of exponents for sure.
Yeah.
Yeah,
So people had to like move downstairs.
yeah. That was.
That.
Like a view or something?
Yeah. When they got
Yeah.
kicked out.
Yeah. You guys remember?
Homeless man who always stays up top.
Well, when no one moves, when no one lives there anymore. Yeah, it's true.
Yeah, the little homeless man who's really good.
Exactly.
No, honestly, that's weird. That better.
So, so here's my function and its inverse, and I want to graph these. Now, what I want to point out is these are both equations of lines. This one, the slope is, what is the slope actually? 3, and the y-intercept b is equal to 1. You might remember that. G of x, maybe I'll rewrite this as g of x equals 1/3 x minus 1/3 if I distribute that. And then you might realize, oh, the slope is 1/3. Oh, undo. There we go. And the y-intercept is 1/3. My goodness. Yes. So let me make a nice little grid here. I'm going to just go 6 by 6 in each direction here. So here's my nice little G-rid. Well, because this wasn't actually in slope-intercept form until I distributed the 1/3 to both of them. Because it's y equals mx plus b, not y equals m parentheses x plus b. So I couldn't just say it's -1. But, right. And that's why the y-intercept was, because I distributed this to both of them. Yeah. So, let's graph our first line, f of x. So the y-intercept is 1, the slope is 3, so up 3 over 1, up 3 over 1, something like that. Or I could even go down 3 backwards 1, right? Down 3 backwards 1 if I wanted. And I'll draw my, you know what? You know what, guys? Here, this doesn't happen a lot, but I'm going to use my little toolbar here. Bam, look at that. I made a line. Guys, I made a line. How wonderful. So, actually, this is just Sketchbook Express. It's not the professional version of the software I'm using. So, just so you're aware, a little behind the scenes, I use Autodesk Sketchbook Express for my drawing tool.
Is there a pro version?
I believe so, yeah. Yeah. I can't review it. This video is not a review of the software, but the Express version works okay. It does what I need. So let's see, b equals 1/3. So here I'd have a slope or a y-intercept at 1/3, and the slope is 1/3. So I'd go up 1/3 over 1. So I'm at like 2/3 here. Wait a minute. Oh, sorry. B was -1/3. Is that what you were telling me earlier?
Yeah.
Oh, I'm a crazy person. Why? I'm sorry.
I'm trying to tell you for so long.
And I didn't understand, but that's okay. You guys were like, crazy Mr. Waddy, he's retiring. That's fine. So here's -1/3. So up 1/3 over 1, up 1/3 over 1, up 1/3 over 1. So I'm like 2/3 high there. Up 1/3 over 1 right there. And let me draw my line tool. Let's see. Looks like something like that would hit it. Bam. There we go. So there we go. So so here's two functions. They're inverses of one another. And you might be like,
Not like parallel for inverses.
well, that's what I wanted to graph these for. There's a relationship between inverse functions that you might not know about. And that is this, that they are mirror images over the line. Oh dear. There, where am I? Wait a minute. What is going on with my grid? Why is like this box right here? Never mind. Wait a minute. Maybe I'm just all crooked here. There we go. I'll just do like this and like this. I'll draw it piecemeal. I just feel like I wasn't hitting the grid in the right spot.
Oh, no, it's because you went from the wrong box.
I did. That must have been what it was. I was all scared again. So it turns out that inverse functions are mirrored over the line y equals x. All right? And it has to do with the fact that in order to be inverse, the x and the y's kind of switch. Notice this point here is like this point over here. Here the x was 1, the y was 0. Here the y was 1, the x was 0. Right over here, the x was 4, the y was 1. Here the x is 1 and the y is 4. So like inverse functions are just kind of like the opposite of each other. The x's and the y's get switched, and that's why we end up having this this interesting setup here.
No, that's so cool.
With the way that works out. So let me have us do this interesting problem here using this concept. Actually, let me write that down first of all. Important fact: inverse functions are reflections of one another over y equals x. Yeah. So important little fact. Bam, 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 bam. Let's see. There's my soggy cardboard box I just put around it. Poor soggy cardboard box. I did a lot of my recycling this week, and I was happy. I got rid of lots of boxes. It's good stuff. So let's do another example. Using that premise, that concept, that fact, let's graph the following inverse,
Oh, there is none.
in which, watch this. Y'all ready for this? Right? Something like that, maybe? I don't know. Seriously, I just got so many subscribers because of that.
How are we supposed to graph something that's already graphed?
Well, if this is, let's call this f of x. So I want you to find f inverse of x, its graph. Actually, I'm
So
going
you
to...
have to find the points on the graph and just do the opposite.
Well, let's just do it by the spirit of it. Let's graph the line y equals x, which is a line kind of like this. Right there. Right, so if you're following along, you don't have to draw this perfectly curved polynomial third degree cubic function. You could just kind of like draw a squiggle and you'll see what we're doing here. And so I want to graph the inverse. And now it's mirrored over the line y equals x. So let's pick some points. So this point right here is going to be mirrored over here.
-0.9.
Yeah. Well, actually it was -0.4 something, because, yeah, the tick marks are half units. Or this point right here, where is this point going to be? It's actually going to be mirrored over the line. To be mirrored, yeah, they're equidistant and perpendicular to the line that it's mirrored over. Actually, that's kind of weird, because then the point on the purple graph that was here got mirrored back over here. Let's figure out where this hill would have been. So here's the peak. Where's that peak going to be when mirrored? That would have been like over here somewhere. All right, is that equidistant, perpendicular, something like? How about this valley? All right, is that far away and perpendicular, so somewhere over here? Is that right? Actually, the peaks are confusing me because they're the same color now. There we go. So it looks like I've got like this direction so far. Now let's see. What about, where would this point be mirrored to? It would, yeah, it would just be mirrored right to itself, because, and like this point would be mirrored to itself. This point would be mirrored to itself. Where would this point be mirrored to? This is about like 2.4. So mirrored this way would be up at like 2.4 on the y-axis this time.
Yo!
Wait a minute. Oh, I keep confusing myself because I'm making points purple on the main function. Here we go. So, and so if I start to connect some of these, I get something like that. And this tail here, if I mirrored it, would be like this tail here, right? Where it's always perpendicular and equidistant from the other one. So I just want to point out, like, you can kind of like just mirror it a little bit over
Yo,
that,
is so cool.
and it ends up working.
It's
So,
actually really cool. I like this a lot.
and one of the things I want to point out is that, yeah, my curve is super sloppy. Well, I don't have a good way to do that graphically. Never mind. We'll talk about that some other time too if we have to. But what I want to point out is that notice the title of this section was Inverse Functions and Relations. Now, relations don't pass a function test, meaning that there's not necessarily one output for every input. And I want to point that out about the inverse here. Was here a vertical line would only hit 1 point. Here a vertical line would only hit 1 point. Here a vertical line could actually hit 2 points and it fails the vertical line test. Yeah, there's multiple outputs. Here's 3 outputs, all for 1 input. So this is the orange is a relation, not a function, although it is still the inverse of the purple one, which was a function. So it's kind of weird. So we've talked about kind of the idea of like how to check to see if something's an inverse using the f of g of x and g of f of x. We understand now the graphs, how those are inverses of one another. But what about algebraically? If I wanted to just like straight find the inverse of something, this is what you would do. How to find an inverse function. And this is if we were doing it algebraically. And then we're gonna do an example of this and graph it. It'll be oh so wonderful, lovely, marvelous. Not about your pen dying. I'm sorry. We'll say some kind words and have a funeral for it later. And just remember all the good times you had with that pen, all the things you learned, like the fact that it gave its life for your education.
My pen came back to life.
Wow, it's a miracle. Yeah.
I really like all the nice advice.
Yeah, it's like I believed in it. It's like I clapped my hands and Tinkerbell came back. Like, it's wonderful.
So it's algebraically?
Yeah, sure. Yeah, you could specify that. That might make the directions a little bit more valuable, I suppose. Yes. Yes.
Sir, why are you being weird today?
I'm sorry. I didn't. Okay.
No, it's okay. It's nice.
Oh, I'm a nice weird. I thought, I don't know. I don't feel any different.
Did you put something in your Cheerios today?
No. No. So, how to find an inverse
Slow down.
function?
My penny's just alive.
Find f inverse of x when f of x is equal to x squared plus 4. Good times. So, the process, step 1 says replace f of x with y. So I'll rewrite this as y equals x squared plus 4, if I'm not mistaken. Right? Step 2, it says switch the x and the y. So I'm going to just like completely switch like some sort of, what was that old TV show, Wife Swap, or like, or what was it, the movie The Parent Trap, when like the two twins switch and it's like, oh my goodness! Or the movie Freaky Friday.
The fact that Lindsay Lohan doesn't actually have a twin like actually blew my mind.
Wait, she doesn't?
No, it's just. But also, like I was watching this thing and they were telling about it, and some of the scenes, they said when she was like, when you see both of them, a lot of the scenes where there's both, one of them is not facing their face because they just took somebody else with the same hand.
Boo.
It's not actually her.
That's disappointing.
And
So,
How can you just switch those?
I just switched them because that's what step 2 told me to do.
Well, I know, but like, how is that meaningful? Scary.
Well, because I'm finding something that's not equivalent, I'm finding something that is the inverse. So the switching the x and the y is actually core to the idea of an inverse. Where, remember, even like when we looked at the graph, the x and the y coordinates swapped with each other?
Yeah.
That's what's happening here algebraically. It's just I switched the x and the y. And now if I want to find this in kind of function notation, I've just got to solve for this new y. So I would do that by subtracting 4 from both sides. And I would have x minus, actually I might flipperoo it. Is it okay? I'm going to flipperoo it here. Y squared equals x minus 4, because I'm now trying to get y by itself. And then what would I do to get rid of the square? Root.
Plus or minus, don't forget.
Oh, we never forget, you plus or minus. So we'd get y equals plus or minus the square root of x minus 4. Now, what I would like to point out is there's one more step, which is really just changing the name of it. You can now rewrite y as f inverse of x if you want. So f inverse of x equals plus or minus the square root of x minus 4. So the core to the inverse is all about switcherooing the x and the y. I was going to try to make that rhyme, but ruin and y doesn't rhyme. So let me show you this graph here. Let's graph both the function and its inverse electronically. And it will be oh so great. So the original function, what was that guy? That was, oh, there it is. X squared plus 4. What is that graph going to look like? Does anyone know? X squared plus 4. Does anyone remember what an x squared function looks like? It's a type of polynomial. It's a parabola, and the plus 4 will actually have given it a vertical shift. So it ends up kind of going right there. Display, I'll make that medium there. So
why is the police?
excellent. So here's x squared plus 4. Now let's graph its function on the same graph. So that's the square root of x minus 4. So I'm going to graph square root of x minus 4. Notice like my awesome little math wordy thing there. But it shows the symbol right. And notice I can't actually, there's no like plus or minus I could put in here. So when I graph this, it's actually only going to graph half of it because the inverse will not be a function. It won't pass the vertical line test because it would be a relation. So the way math solves it on its own, graphically speaking, is it will graph just kind of half of the parabola, which this half would pass the vertical line test. Let's see, display style medium. And let's make this, ooh, a nice little crispy orange there. Actually, crisp apples are good. Crisp oranges. There are ways I can reflect stuff, but what I'm going to do is actually just graph another function, which is going to be the negative version of it. So I'll just throw a minus sign out in front, and then hit OK, and then hit graph, and bam, there we go, friends. Look, we've got our two inverses, and they are, turns out, they are mirrors of one another over the line y equals x. And look.
Why is the orange one so short?
Because yeah, sometimes the graphing tool it does that. Yeah, I can get it to be longer if we wanted to. But yeah, so these are mirrors of one another over the line y equals x, and it's oh so wonderful, isn't that great? Inverse functions.
Very true, very true.
Yeah, yeah. If I zoom out, like you see the arrows ended there for actually all of those. I think I can actually hit this and hit this and delete this. And if I select these and hit graph, bam, it'll give me the rest, more further arrowness of it. But anyways, that's just some Geometer Sketchpad stuff. This is the pro version of Geometer Sketchpad, by the way. It's GSP 5, if you're wondering. It's got some pretty cool features. So thanks for watching, internet friends. That's everything I feel like telling you about inverse functions for today. So have a great day, friends. Bye-bye.